So first, if we just take this idea of adding and subtracting molecular orbitals, atomic orbitals to make molecular orbitals, what do these roughly look like? Well, one way we can kind of plot this, of course, these are three-dimensional, so it's a little bit hard to visualize them in two-dimensional drawing like I'm going to have here. But let's take just if we have our one electron, let's look at a 1s orbital. If we kind of plot this along one particular axis, right? So, of course, this is a spherical probability distribution. But a 1s orbital has this e to the minus r term. So if this is our nucleus here, we can kind of plot this as this will have some value at the nucleus as where it's largest, and then we get an exponential term. And because r increases, right, r can never be negative, it always increases. We get sort of this shape like this if we're looking at this in terms of r, right? Of course, this is spherically symmetric, but we get sort of this shape like this, where it kind of goes to a maximum, and it's not really well defined at the nucleus, but decreases exponentially from there. So if we add them together, so what we'd call psi plus, we're going to get something where we have our two nuclei, and we'll still have this shape like this, and it'll go down, but it'll increase again here, and we'll see something like this, right? So and these will both be in phase, positive. All right, so we'll have some electron density close to nucleus A, some electron density close to nucleus B, and some shared electron density between them. This is what we're used to thinking of as a bond, right? This is what we consider a bond, is that our nuclei share their electrons with each other, and this is showing up quantum mechanically. What about the other molecular orbital? Right, we can take two of these and subtract them instead. And so say our positive one is on nucleus A, our negative one is on nucleus B, we'd have something that looks roughly like this. Drawn, not exactly correctly here, but we'll have a positive on this side, negative on this side, and we see that there'll be a place where the wave function will go to 0 and makes a node in between the two nuclei. And this is the opposite of what we usually think of as a bond. They're not sharing electrons, they're sort of keeping them to themselves. Now let's look at the energies associated with these wave functions. If we want to find these energies, we know how to do that. We use variational theory. And so we can write out that our energy for these plus minus wave functions that we have, these will depend on the internuclear distance, on the bond length. And so this will be equal to the integral of our psi plus or minus star. We've written out our Hamiltonian. We can use that Hamiltonian. It's only 4 terms, but it's still 4 terms to worry about. So this is not a trivial problem to solve. But this is a solvable variational theory problem, and your textbook goes through this, but we're going to skip to the results. And then, of course, we divide by the normalization integral here. Right. So each of these integrals is, of course, in 3 dimensions in spherical coordinates, and so it takes a little bit to solve it. But this is going to depend on r, right? How exactly these wave functions look when they add together is going to depend on how far apart a and b are, right? So for example, if a and b are really far apart, the wave functions really won't overlap at all. They'll overlap a little bit out here in the middle, but these are almost like 2 separate wave functions. But when they get closer, these wave functions start to overlap. And so that'll be reflected in our approach here. So according to the Born-Oppenheimer approximation, we can, at each value of r, we can find, what is the energy associated with that wave function. And so that's what this plot is showing here. So we'll have energy on the y-axis and our bond length r on the x-axis here. So if we look at our energy for psi plus, it looks a little something like this. It starts positive, goes down, dips below, becomes negative, and then asymptotically approaches 0. And I didn't draw that very smooth there. Let me just maybe fix that a little bit. Oh. Well, I'll just give myself another try. That's better. A little bit more smooth there. Okay. And what I'll say is energy equal to 0 represents the two atoms separated. Right, represents the energy of all the separate atoms, right? So in this case, an hydrogen atom and a proton, H+. And then our psi minus energy looks something like this. So this is figure 9.6 from your book, if you want to see a more proper drawing of this. The key point here is that we have an energy here that is below the energy of the atom separated. We formed a bond, right? The energy is lower than separate atoms. And this is a bond. All right, and the psi minus wave function, the energy is always higher than the separated atoms. So if the system is in the psi minus wave function, it'll prefer for the atoms to separate, whereas if it's in the psi plus wave function, there'll be a preference for the atoms to stick together and stay as a molecule. And this is, just with one electron that's holding the system together. And this arises from, quantum mechanics. All right, in the next section, the next video, we'll finish up looking at H2+, looking at the probability distributions of the electrons.